Okay. So, in the previous lecture we stopped at this plot, a plot of bit error rate versus EB over N naught for uncoded BPSK, and I was claiming this is the curve. For instance, at 10.5 dB of EB over N naught, we have a bit error rate of 10 power minus 6, and coding is going to help you move this curve to the left, maybe at a lower rate than 1, but it can do that. Okay. So what we are going to do in this lecture is multiple things. First is this course will involve some programming language. Okay. So I am not very particular on which one you should use, you can use the one that you like, but what we will demonstrate in this class will be MATLAB or its equivalent or clone or limited clone, which is the GNU Octave program. Okay. So now MATLAB is licensed, you may have to get a license for it, your institution may have it or your organization may have it. If it does, you can use MATLAB. If you do not have such a license, you can download Octave for free. It is a free and open source software, and you can use it. The reason why I am sticking to MATLAB Octave is it has a common syntax and it is easy and many people know it. So, that is why I am doing it. But none of the assignments will actually require you to stick to MATLAB, but you should do some programming. You might use Python if you like, or C if you like. You will have to write some programs, but what I will show you, what I will demonstrate to you in class will be MATLAB and Octave also. I will use both just to show you how they are both quite equivalent. Okay. So, to begin with that, in this lecture we are going to see a couple of things. One mainly is how to generate this graph. Okay. We will see that using MATLAB and Octave as well, and then how to write a quick simulation to validate this graph. Okay. So, this graph for instance predicts at 4 dB, at 4 dB of EB over N naught, it predicts a bit error rate of around 10 power minus 4 dB, comma, I don't know, so roughly around 10 power minus 2, right. So, how to validate this point? Okay. So, how do you validate it by simulation? So, we will write a quick small simulation to check what will be the error rate at 4 dB of EB over N naught. We will do it for the uncoded BPSK case. It is good to keep this program with you, because soon enough we will add coding into this program, and at that point you can keep the rest of the framework the same. You just have to change some encoding and you can keep using this framework. So, the little piece of code we write today, which is the simulator for uncoded BPSK, is very useful for the entire course, and we will build on it and eventually have our encoders and decoders for LDPC codes and turbo and polar codes written as part of that program. Okay. So, let us get started. So, I am going to show you first which has MATLAB. So, this is how MATLAB looks. It's of course like I said, it's licensed software, so you need to get a license for it as well. And I'll show you how Octave looks. Okay, and this is credits for Octave. It's free and open source, distributed under GNU's license. There's no warranty and things like that. That most software comes with no warranty, but it's free, right? So you can just do that, and most of the software, the programs and code that we will write in this class will require only elementary use of computing platform MATLAB. We won't use any of the inbuilt packages. We will write everything from scratch. So most of the things I write, you will be able to run it on Octave just like that as well. Okay. So, just for completeness, today I will show both Octave and MATLAB. Going forward, maybe we will stick to one of the two just to keep things simple. Okay. So, let us get started. The first thing I want to say is about this Q function. So, let me say a few words about what this Q function is. Like I mentioned, you have this Gaussian integral, right, and then this is the Gaussian PDF, which is 1 by root 2 pi e power minus x squared by 2. Okay. So, this is the 0 mean variance 1 Gaussian PDF. So, maybe I should write this 2 pi a bit more clearly. Okay. And if you keep if you fix a point like say x naught, okay, q of x naught is defined as integral from x naught to infinity of this function 1 by root 2 pi e power minus x squared by 2 dx. Okay. So, this is the function that we have to implement to be able to make that plot, and that plot was with q functions. Now, it turns out many, for instance MATLAB has a package which will evaluate the q function for you, but we do not have to use that package because there is another function called ERFC, complementary error function of x naught, which will look very similar to this. In fact, you can go to MATLAB and type help ERFC, which is what I have done here, and you see ERFC is very similar to q. You can see what it is here. It is 2 by square root of pi integral from x to infinity of this. Okay. So, this you can see is sort of similar. So, let me write it on the other page and we will see how to manipulate one to get the other. It is quite straightforward. I will show that, show how to do that. Okay. So, let us, so this function is 2 by square root of pi integral x naught to infinity e power minus x squared dx. So, if you stare at these two very closely, it turns out q of x naught is 0.5 times ERFC of x naught by square root of 2. Okay. So, you can check that. So, how to how to prove this? So, you will have to do a substitution here of x equals x by root 2. Okay. If you do that, this will become integral x naught by root 2 to infinity 2 by root pi e power minus, you will get the x squared by 2 that you want. This will be 1 by root 2. Okay. So, this 1 by root 2 will cancel here and you will get a root 2, but you need a 1 by 2 root 2. So, you need a half. So, this is a formula that I am not going to give you more details of. Please check this. If you do this substitution here, you will get this equality. Okay. So, 0.5 ERFC x naught by root 2 is q of x naught. Okay. So, this is a good thing for you to remember. I think I had put this up in the previous slide as well. The nice thing is ERFC is natively supported in most platforms. You will have a function for it and you can write a quick conversion to q. Okay. So, you can keep this in mind. So, once we have this, we are ready to write our little piece of program to generate the curve.